Today we're going to look at the sampling distribution for the difference in two sample proportions. We use this to test for the equality of two population proportions or to estimate the difference in two population proportions. The conditions for this sampling distribution are that we have to have two independent simple random samples, one from each population. Each population must be at least 10 times its respective sample size, and the success failure conditions have to be met for both samples. Now, if these conditions are met, then we can say this about the sampling distributions for P1 hat and P2 hat. P1 hat will be normally distributed with the mean equal to P1, the true population proportion, and the standard deviation equal to the square root of P1 times 1 minus P1 over N1. And P2 will have a similar distribution, will also be normal, with a mean of P2, its corresponding population proportion, and the standard deviation of the square root of P2 times 1 minus P2 over N2. Now, if we have two independent simple random samples, P1 hat and P2 hat will be independent. That will be very important in what we're about to do. And what we want to see is how is this difference in sample proportions distributed. We want to be able to describe it in terms of its center, its spread, and its shape. Let's look at the center first. Basically interested in the mean of the difference in sample proportions. Well, the mean of the difference in sample proportions is equal to the difference of the means of those two sample proportions. And the mean of P1 hat is P1, the mean of P2 hat is P2. It means if we're using this difference in sample proportions to estimate that difference in population proportions, our estimates will be unbiased. P1 hat minus P2 hat is an unbiased estimator of P1 minus P2. Secondly, the spread. Here we rely on the fact that the two sample proportions are independent. Okay, that's very important. That's why we have to have two independent simple random samples. Okay, the variance of the difference in the sample proportions is equal to the sum of the variances, variance of P1 hat and the variance of P2 hat. Now we know what those variances are from the sampling distributions for P1 hat and P2 hat. They are P1 times 1 minus P1 over N1 for P1 hat, and P2 times 1 minus P2 over N2 for P2 hat. And then to get the standard deviation, we take the square root. It's a big square root with a big expression underneath. And this is one of those situations where maybe using a calculator is going to be a lot easier than trying to do this by hand. And thirdly, the shape. Okay, if the conditions are met, P1 hat and P2 hat are both normally distributed, and P1 hat and P2 hat are independent. If that's the case, then the difference of P1 hat minus P2 hat will also be normally distributed. So that takes care of the shape. And this is the summary. P1 hat minus P2 hat is normally distributed with a mean of P1 minus P2 and a standard deviation equal to the square root of P1 times 1 minus P1 over N1 plus P2 times 1 minus P2 over N2 if the conditions are met. Now let's look at an example. Suppose we know that P1 and P2 are equal and N1 is 500 and N2 is 400, and all the necessary conditions are met. Suppose we want to find the probability that if we were to calculate the two sample proportions, they would be different by more than 5 percentage points. That is, the probability that P1 hat minus P2 hat is greater than 0.05. Well, this variable right here, P1 hat minus P2 hat, is normally distributed if all the necessary conditions are met, as we're assuming, and we can standardize this inequality right here, and then we can figure out the probability using a z-distribution. So first we need to know the mean of P1 hat minus P2 hat. Well, it's P1 minus P2, 0.4 minus 0.4, which is 0. The standard deviation is the square root of P1 P1 times 1 minus P1 over N1 plus P2 times 1 minus P2 over N2. And if we plug in all of our values and simplify, we get 0.0329 for that standard deviation. Now we can standardize that probability expression from up above using this mean 0 and the standard deviation 0.0329. And instead of writing all those letters and numbers and hats, I'm just going to replace everything with a z and assume that we standardize that side. And then the right-hand side, we standardize the 0.05, and it'll simplify down to 1.5215. So we're looking for the probability that we get a z statistic or z-score that's greater than 1.5215 in this case. And that works out to be about 0.0641. So about 6.5% of the time, if the true population proportions are equal, you'll still get a difference in sample proportions. It'll be greater than 5 percentage points.